Okay. Good afternoon, everybody. It is a pleasure for me to introduce Professor Abdolrahman Razani from IMA Comini International University. Professor Razani is a researcher who has more than 180 publications, and some of them with Brazilians. Professor Razani, thank you very much for agreeing to participate in your seminar. Please, Professor Razani, now it's your turn.
Okay, let me thank you. I would like at first thank you, Giovanni and Sandro and the other organizer that inviting me to have to be in this opportunity to be in this event and give a lecture about my research topics. And my research topic in these days is about the study of quantum uncertainty principle. And 2 days I want to talk about it and the Heisenberg group and the Sub-Laplacian operator and how mathematically we can make a bridge between these three concepts that I told you about. Okay, let's go to the talk. And I mean, at first I try to start to talk about a little bit about quantum mechanics and the history about the problem, and then we talk about the Heisenberg group, and so on. We go to the horizontal subtle of a space and how the embeddings working in this kind of spaces, and then finally we try to say something about the graded Lie group and the eigenvalues. And meanwhile I try to introduce you some good problems or challenging problems in someone interested can work on that. Okay, the story of the quantum mechanics, I can say, went back to the early 19th century when Max Planck wanted to study about the black body radiation. He tried to introduce a constant which is called the Planck's constant. You will see here, and by this constant is very famous. Because the quantum mechanics in those days there were some issues about the studying of some problems in nanoscale size. In nanoscale size, the classical rule of physics are failed. So they need to study something that can solve the problems in nanoscale size. And when Max Planck introduced this constant as a Planck's constant, by this constant, Einstein tried to introduce his famous formula, which is the relation between the frequency and the energy of a photon. And after that, Heisenberg and Schrödinger tried to introduce two versions of quantum mechanics. One of them was the matrix mechanics, which was introduced by Heisenberg, and another one was the Schrödinger wave mechanics, which introduced by the Schrödinger equation in the quantum mechanics. We will focus on these two versions right now, and we talk about it more in details. But before that, I would like to say something about the why this constant, I mean the Planck's constant, is important, because the Planck's constant is something like 4.3566 blah 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 blah, and if you round the first digit numbers, it can be say is 4.14. I mean, if you round the first digit numbers of the Planck's constant. So if the first 4 is the fourth month of the year, and the 14 is the 14 days of the month, so the April 14 of each year is called a World Quantum Day. And this shows that how much this constant is important. And why they try to introduce day as a quantum day, because they try to count all the events around the world during the year. I mean, for example, it started in 2022, and in between 2022 and 2023, there were about 200 events in more than 44 countries. And from 2023 to 2024, it increased to 400 events, and this shows that they want to know how much the quantum takes place in the daily lives of the humans. So maybe later they will come for 2024 that this goes to 800, something like that. Okay, after this history, I want to go to the wave mechanics and introduce you the here I am is very concise because I just have a good abstract about the quantum mechanics for us. We can have it in the later in some slides. There is a slide you will see that which is called as a Schrödinger cat. In this slide you will see a box and a cat, and there is also a cat, there is a radioactive substance, there is a detector, there is a Homer, and there is a glass of points. What is the issue? The issue is that you have all these in a box, and you want to close the box, and after a certain time you want to open the box. So what do you expect to have? I mean, this is I am going to say that this is a thought experimental example, not real example. This is a discussion between Einstein and Schrödinger. So what do you expect to have? Maybe we expect to have two options. The one option is that if the detector doesn't detect any radioactive radiation, so the Homer doesn't work and then the cat is alive. But if the detector detects any radioactive radiation, so the Homer is work and the cat is dead. So there is two options that we can say, but is there a possibility that when we want to open the box, the half of the cat is alive and half of the cat is dead? We don't know anything. This is uncertainty principle, I mean, because the radioactive radiation is a discontinuous process, and this discontinuity jump depends on the Planck's constant. And when we close the box and before we open that, if we are in the interval of the discontinuity, it means that the Homer doesn't work. But if we are not in the discontinuity process, it means that the Homer works. So what we don't know what happened, and just we can say as a vector there is a two, one of x, one of them is y. X is for dead, y is alive, and any vector in between of these two in this region is the possibility that we have. So Schrödinger says that you can say there is a superposition of all possibilities that you have, and when you open the box, your observation confirm which of them will be happen. This is a version of the quantum mechanics which is called wave mechanics. Okay, let's go to the next one about another uncertainty principle, which is called about exact precision about momentum and position. What does it mean? It means that if you have a particle, you cannot simultaneously be exact in the position of a particle and exact in the momentum of a particle. If you are exact in a position, you are not exact in momentum, and if you are exact in momentum, you are not exact in position. Let me give you an example to be more familiar with the subject. But the subject, if you want to be very familiar, it should be in the nanoscale size. But we cannot present it here, so I try to present an example in a real size because we can have a good intuition about the problem. So you will see some days in the volleyball game, the referee says that please do the video check. What does it mean? When they do the video check, it means that they make a picture of the ball. When they make a picture, it means that they freeze a ball somewhere, and when they freeze the ball somewhere, it means that they can find the exact position of the ball. But when you freeze the ball, you cannot say anything about the speed of the ball. This is uncertainty principle. But if you want to say something about the speed of the ball, you cannot say something about the exact position of the ball. This is a good, I think, example that we can have a good institution about this uncertainty principle. Let me give you another example. Maybe it is better. In this picture, you will see, for example, one man is running and you want to make a picture of that man. It depends on the shutter speed of your camera. If the shutter speed of your camera has a good quality, then you have this picture. It means that you know the exact position of the man, but you don't know about the exact speed of the man. But if the quality of the shuttle speed of your camera is not good, it means you have in this position, you can say something about the exact speed of the man, but you cannot say something about the exact position of the man. Where is the man? The man is somewhere in this shadow. Just you know that somewhere in this shadow, but where is it? You don't know. This is something that they say this is uncertainty principle. So by this version, as I told you, there are two versions of the quantum mechanics. One of them was wave mechanics, and the another one was matrix mechanics, which was introduced by Heisenberg and by this uncertainty principle. So at the beginning, it was a challenge that these two versions of the mechanics are different, and this is a very big deal for physics. But good to mathematics, and there is a very nice theorem in 1930 that which is called Eston von Neumann. This theorem says that these two versions of the quantum mechanics are equivalent to each other. In fact, this theorem says up to isomorphism, there is a unique irreducible unitary representation of the Heisenberg group with that central character. It means that two versions of the quantum mechanics, matrix mechanics and wave mechanics, are equivalent to each other, and this is good because we can say, okay, the problem is solved for the physics, and also we know that by this version we can say everything in the quantum mechanics by Heisenberg version, and this is why that we switch to the Heisenberg version and we try to talk about it. Okay, after this introduction, we go to introduce the Heisenberg version of the quantum mechanics mathematically. I can say that we need this kind of mathematics because in these days, you know that you want to solve many problems in a nanoscale size. If you want to solve the problems in a nanoscale size, it means that the traditional mathematics cannot plays a good role for you. So you need to have a good mathematics, has a good structure, which has uncertainty principle inside of that. So let's go to this problem and how we can introduce this uncertainty principle mathematically. Let's consider a group of 3 times upper triangular matrices with operation of multiplication. You know that this group is a non-abelian group. Yes, because of this parameter. It means that if you commute these two elements with each other, that this element can be, different. So this is a non-abelian group, and this is good for us. Why? Because if I try to introduce a group of 3 times 3 matrices as this form, which is a triangular matrices, and try to introduce 3x, x, y, z as a base for this algebra, then there is a good property of these 3 bases, which is the bracket of x and y is z, but the bracket of x and z and the bracket of y and z are 0. What does it mean? It means that x and z, y and z can commute with each other, but x and y cannot commute with each other. You see, because the bracket of x and y is equal to z. This is something that it is very nice for us. Why it is nice? Because if we try to define a corresponding function and introduce x as a position of an operator and p as a momentum of an operator, it means that the bracket of x and p is z. H is a Planck's constant. So it means that you have a good uncertainty principle in your mathematics. By Lie algebra here that I introduced, I have an uncertainty principle inside. So this corresponds, you can define the combination of two elements of this, two odds of this, H as a Lie algebra by this relation, So this came out from the Baker-Campbell-Hausdorff formula. If a to power a, e to power a times a to power b is defined by a to power a plus b plus half of bracket of a and b. By this, I have everything which is good. Let's go to the R instead of H3 to Hn, which is based of R2n plus 1. It means that I have xj, yj, t as a vector fields, and by these vector fields I can define the horizontal vector field which is spanned by these vector fields. So the good properties, as I told you, is the bracket of xj and t, the bracket of yk and t is equal to 0, but the bracket of xj and yk is Kronecker delta. It means that if j is equal to k is 1, as you know, and if j is not equal to k is 0. So I am in a good position, so I have everything that I have. I wanted that, so I can define the, sorry, I have to again say that I am very concise to have time to present some new results in this topic. Because of that, I am too fast about introducing some notation. Now I introduce the gradient, and as a normal that we have the normal mathematics, and by the definition of the vector field, we have the gradient, and when we have the gradient, we can define the Laplacian, which is called in this setting Cohn-Spencer Laplacian or horizontal Laplacian. Okay, the definition of the Laplacian in this setting, in the Heisenberg setting, is the normal definition that we have in Rn. This is the summation of the square of the vector fields that we have. And the representation, exactly if you put xj and yj as we had before, you have this kind of representation of the Laplacian in the Heisenberg setting. And we know with a very good theorem by Hormander that the solution of this operator is very smooth. If delta of u is c infinity, then u is c infinity, which is called hypoellipticity. We will be back to these properties again later. So let me give you an example in H3. In H3, when we wanted to introduce the Laplacian in H3, if you represent the Laplacian in H3, it has two parts. One blue part is the Laplacian in R, and the red part is the Laplacian in H3, which is the one that I introduced you in the last slide. And this is the one that we call it as a Sub-Laplacian. The Sub-Laplacian is different from the Laplacian you will see here. We don't have the last term in this summation for the Sub-Laplacian. And this makes a very good property for the Sub-Laplacian, because the Sub-Laplacian is sub-elliptic. But it is not elliptic. You need to be more careful about this. And we will back again to these two properties later, because this is about the regularity of the solution, and we can say something about the smoothness of the solution of the problem. So when we have the Laplacian, let's go to the Rn. Then we can define the P Laplacian, and we can define the Sobolev space as normal that we have in the Rn. And again, you can define the norm and show the normal theorems are valid. The Sobolev space is a Banach space. Here, this W1P is a Banach space and is uniformly convex, and etc. All the properties that you needed, you can present it here. When you have these Sobolev spaces, in order to study your problems, you need to have some embeddings theorem. This kind of embeddings theorem is proved. I mean, this is something up to my knowledge is correct in this kind of setting. You can prove that this embedding for Q between P and P star is continuous, and when Q is less than P star is compact, when P star is some number like this, when the capital Q is the homogeneous dimension of Hn. This is not the problem, but my question was happened when I wanted to study anisotropic horizontal Sobolev space. What does it mean? I mean, consider a vector P as a P in the definition of the P Laplacian. And each of these PI has own direction, and they don't necessarily have the same direction. Each of them has their own direction. So this is make a good difference by isotropic version. If you define this anisotropic version of the horizontal Sobolev space by this definition, I mean, you can define the definition of the Heisenberg P Laplacian in the anisotropic version, and then you can define again the definition of the Sobolev space in the anisotropic version, and again you can define the norm of this space by this one. And when you have this, again, something that happen is, do we have the embeddings like that we have in the isotropic version? This is the question. The question was good for me because I tried to study this question because of wanted to study a problem in this setting, and I faced with this question, and I tried to prove that, but I couldn't. And so I tried to make a conjecture about when Q, what we can say when this embedding is continuous and when this embedding is compact. And I try to make this conjecture. If someone in these two papers, there are some results about this kind of conjectures. And if someone interested can study these problems, because I think if you can say something about this kind of embeddings, that it makes you the possibility to study the problem in anisotropic setting. This anisotropic setting has very good is very useful for industrial problems. The engineering like to study this kind of problem, which each PI has own direction, not exactly they have the same direction. This makes me to study, because I couldn't solve this problem in this kind of setting, so I try to go to a more general one and study some problem in the to help me to prove these theorems. Because of that, I try to study the graded Lie group. The graded Lie group is a group which is a vector space decomposition of Vj, which the bracket of Vi and Vj is a subset of Vi plus j. For example, and the Lie group is graded when it is connected, simply connected Lie group with whose Lie algebra is graded. As an example, Rn with operation plus is a graded when V1 is Rn and the others are trivial. And the Heisenberg group again is a graded Lie group, which can be as a V1 plus V2, where V1 is the summation of X and Y and V2 is T. I mean the last vector field. By this, so the graded Lie group is a good setting to study this type of the anisotropic setting. And why we need to study this? Because if you need to study some power of the Laplacian or some power of the sub-Laplacian problem, you need to study this kind of setting. Why? Because if we consider the definition of the Rockland operator, which is a left invariant differential operator, which is homogeneous of positive degree and satisfied the Rockland condition. What is the Rockland condition? It means that for each unitary irreducible representation of pi on G, it is injective, I mean. So it means that we have this kind of condition. So what is, as an example, to be more familiar with the Rockland operator, any power, as I told you, of the Laplacian, any power of the Laplacian or any power of the sub-Laplacian is a Rockland operator. And again, a theorem by Hormander guarantees that any sub-Laplacian is hypoelliptic. It means that Rockland operator is hypoelliptic. So this is very good. So if I wanted to study any power of the Laplacian or any power of the sub-Laplacian, it means that I need to study the Rockland operator on graded Lie group. When I wanted to study the Rockland operator, I need to study the problem on the graded Lie group. Let me show you a picture. This picture makes the problem more clear. It means that you know that Heisenberg group is a subset of the graded Lie group. So if I wanted to study a problem, maybe I study some problem in the graded Lie group, which is not in the Heisenberg Lie group, you know. And when I wanted to study this kind of problem, because I told you I was interested to study some power of the Laplacian and some Laplacian, I need to study the problem in the graded Lie group. And when I wanted to study the problem in the graded Lie group, another problems comes in, which you need to think about the regularity of the problem, the solution of the problem, because you know that as when we are in the graded Lie group, it means that we are here in the sub-ellipticity side and maybe hypoellipticity side, not exactly in the ellipticity side. So this is maybe makes better for us, I don't know, but this is the problem. So what is the question here? The question exactly here, those two embeddings theorem that I told you in anisotroping settings, again, can be works in the graded Lie group, and can we say those kind of embeddings in this kind of setting? This is some question in this side that maybe if someone interested can think about that. This is something about I think the first part of my talk, which is I try to say something about the representation of the embeddings theorem in the setting of the Heisenberg, and finally in the graded Lie group. But now I wanted to switch to another problem, which is related to again to this one. Another problem is that to study an interesting question in spectral theory. What is the problem? The problem is that what is the relation between the Neumann-Laplacian and Dirichlet-Laplacian? What does it mean, Neumann-Laplacian and the Dirichlet-Laplacian? This means that I mean the Neumann-Laplacian and the Dirichlet-Laplacian is the Laplacian with the Neumann boundary condition is called as a Neumann-Laplacian. But the Laplacian with the Dirichlet boundary condition is called as a Dirichlet-Laplacian. Okay, why this kind of question? I mean, this relation between the eigenvalues of these two problems is important because I think because of three questions I can say. One of these questions is a study of nodal domain. It means that when you want to study a problem and the solution change sign, if you know something about this relation can help you to study the problem in a nodal domain. Another good point of this problem is when you study the maxima or minima of an eigenfunction. Again, if you say something about this relation, maybe helps you to study about the maxima or minima of the eigenfunction. And the last one, when you want to study the hot spot conjecture, again, if you know something about the relation between Newman-Laplacian and Dirichlet-Laplacian, helps you to say something about this hot spot conjecture. What is the hot spot conjecture? Let me be more precise. Hot spot conjecture is was presented by Geoffrey Rush, as it is a well-known mathematician, and you know all familiar with this guy, I think. For example, you have a piece of metal, and at initial point or initial condition, each point of this metal has own direction. What is the question? The question is that after a while, is there a point which is the coldest one and which one is the hottest one? I mean, can we say that there is a point which is the coldest one from the temperature point of view and the point which is the hottest one? This is the problem which is introduced by Geoffrey Rush in 1974. When D is open connected boundary with Lipschitz boundary, they try to say something about this problem, and the eigenfunction corresponding to the second eigenvalue of the Laplacian with Newman condition attain its maximum on the boundary of the domain. So this, if you can say something about the relation between the Newman boundary condition and Dirichlet boundary condition, maybe you can say something about this problem. Okay, again, I introduce exact state of the problem. The statement of the problem is that if you consider mu I as the eigenvalues of the Newman Laplacian, and if you consider lambda I as a eigenvalues of the Dirichlet Laplacian, by classical variational principle, you can say that mu k is less than or equal lambda k for k belongs to natural numbers, I mean. So it means that you know how many of the eigenvalues of the Newman problem are less than or equal the Dirichlet problem. This is something that you can say by classical variational principle, but let's go back to the problem exactly when it was started. The problem was started by Puglia in 1952. We are in R. Here, D is equal to, so we are in R2. When D is equal to, it means that we are in R2, and Puglia proved that mu2 is less than lambda 1. It means that mu1 and mu2 are less than lambda 1. So two of them are less than lambda 1. And 3 years later, Pine in 1955 proved that if omega is convex with C2 smooth boundary, then prove that mu k plus 2 is less than lambda k for any k belongs to n. So this is a good generalization of Puglia's theorem, I mean. You will see here. Now go further. About 1986, Levin, Weinberg, and also I will show independently prove that if omega is a subset, convex subset of Rd, whose boundary is C2 smooth boundary with Holder continuous second derivative, then mu k plus d is less than lambda k, which d is the dimension of R. And also they proved that for certain non-convex domain, if R with R depending on the curvature properties of the boundary, they proved that mu k plus R is less than lambda k when R is less than d. And by approximation method, they proved that mu k plus d is less than or equal to lambda k for any convex bounded domain omega. Okay, after this result, I can say a breakthrough was made by Friedlander. Friedlander in 1991 prove that without any curvature assumption on the boundary, that mu k plus 1 is less than or equal lambda k. This is something that Friedlander proved. And after that, let me say something about the Friedlander's proof. The Friedlanders try to prove the existence of any lambda positive of a function u such that satisfy in this kind of equation, which function is provided by this kind of representation. This is the proof is based on the existence of lambda satisfy in this kind of relation. But after that, Filinov in 2005 proved that mu k plus 1 is less than or equal to lambda k in fully generality, I mean. But exactly he did nothing, just he simplified Friedlander's proof and removed the smoothness assumption on the boundary. So this is the progress of the problem, I mean. And in 2023, when omega is a subset of R2, which is bounded, simply connected Lipschitz domain, he proved that mu k plus 2 is less than or equal lambda k. And this is a good, I mean, up to now, good version of the problem. And he proved theorem by variational method, I mean, this theorem. But it's still open. I mean, I can say this is still open, that can we say mu k plus c is less than lambda k for any arbitrary domain in RD or for non-convex domain in RD? This is something that which is still open. Some problems came to my mind that can we start this kind of problems in the Heisenberg setting. Because of that, I found a problem that Mazov in 1991 studied this problem in the non-Euclidean space, I mean in the hyperbolic space. And he can prove that mu k plus 1 is less than or equal lambda k. And in 2010, in H3, please note that in H3, Frank and Lapatov proved that mu k plus 1 or less than or equal is less than or equal lambda k for any k in N. And the novelty of their work is to again construct a function u which is the solution of this problem and is satisfied in this boundary, in this bounded condition, I mean. Again, they prove that if omega is subset of Hn of finite measure, then the total spectral multiplicity of the operator is satisfied in this interval. So is less than, k plus 1. This is good problem that Frank and Lapatov proved that, and they prove also this the structure of the proof is the same of the structure of the Friedlander's proof, I mean just in the Heisenberg setting. The question that I wanted to study in this kind of setting, and I'm trying to say something but I couldn't again, and this is the problem in progress that I'm working on that. Can we say that mu k plus q, which is q is the homogeneous dimension of the Heisenberg, is less than lambda k for any arbitrary bounded domain in Hn? If we can say something about this problem, it means that we are in a good side. So we can say something about the relation between the eigenvalues of the Neumann boundary condition and Dirichlet boundary condition. And this problem is, I think, up to my mind, is very important. If you say something, again, we say something about the nodal solution and the maxima or minima of the eigenvalues in the Heisenberg setting. And as I wanted to be more precise, we need this kind of mathematics in these days because this kind of mathematics has uncertainty principle inside with in its structure. What does it mean? It means that you can solve the problem in nanoscale size by this kind of mathematics, but not real mathematics. I mean, yes, maybe sometimes you can solve the problems with those kind of structures, but this is the structure that has uncertainty principle inside. This talks that I try to present it to you is based on this kind of references that I published. One of them is with Professor Giovanni. I mean, the fourth one, and the others also I'm alone. And if someone interested, maybe can check some of these papers to be more familiar with the subjects. Okay, I think my time is over, and thank you very much for your attention. Any comments, question? Thank you.
Okay, thank you, Professor Razani. Some questions? Remarks? Razani, I have a question. In general, what is the regularity of solutions of the Sub-Laplacian operator?
Sub-Laplacian? Sub-Laplacian.
How about
okay, the regularity of Sub-Laplacian? The Sub-Laplacian is a sub-elliptic operator, but is not elliptic operator. This is something that we can prove that the Sub-Laplacian is a sub-elliptic. You know, and because I show in one, I can back here. You have my. Sorry. Do you have my the screen? I mean, I think no. Yes. Okay. I mean, can you see my PDF file?
Yes, we have your screen, but only the last slide. Thank you.
Oh, let me share it again. Maybe I can. Okay. Yeah, let me share it again. Sorry. Oh, maybe I close it. Let me. Because of this question, I would like to show you. Do you have it?
Not yet. Yeah, yes. Now it's yes, it's open.
Oh, okay. Let me come back to this slide. I want to come back to this. Okay, here. Okay, here. You know, here, when we are studying the Sub-Laplacian, in the Heisenberg setting, we are in the sub-ellipticity side, but we are not ellipticity. So this is the regularity of the solution that we have about the Sub-Laplacian. Again, if you generalize the concept of the Sub-Laplacian into Rockland operator integrated this group, then you can say something about the sub-ellipticity and the hypoellipticity, but you cannot say anything about the ellipticity regularity of the solution.
Okay. And is there a maximum principle? No.
No.
Okay. Thank you very much. More question?
Some question. Good afternoon.
Yeah, Hernan, please.
Thank you. I would like to know about the connection of your results with the original problem of the Heisenberg uncertainty, the Heisenberg incertidumbre, no? What is the connection?
If I get you correctly, I repeat your question. Your question is that what is the relation between a solution in the Rn and in the Heisenberg setting? Yes?
Yes, yes, all right.
Okay, if this is the question, my answer is that, as I told you, a big problem in the Rn is when you study a problem in Rn, you need to think about the study with the classical rule of physics. But if you want to study a problem in a nanoscale size, you need to study a problem in a Heisenberg setting, because the Heisenberg setting has uncertainty principle inside. This is the problem that at the beginning of the quantum mechanics makes place, and this makes difference between a solution between the Rn and a Hn, But let me say something. If your problem in Hn has in a real size, that your results confirm the results in Rn.
What is the principal role of the inequality, the principal inequality of the Heisenberg, that the position and the position and the momentum, that equality, what is the principal influence? Is tan important that hypothesis, the Heisenberg?
Excuse me, I didn't get you well. Sorry, I didn't get you well. Sorry.
The inequality. Okay. No, I am talking about the inequality. The mechanical principle of the Heisenberg is the inequality. The position is not definite. The two quantities physical, but that condition I don't see you use in your demonstration, in your proof.
Okay, let me show you if I get you again your question correctly. Let me goes back again at the beginning of my slide. The problem in the Heisenberg setting was that this kind of inequality, it means that the variation of the position and the momentum are not zero. This is something that we want to know. But this part is not very important for mathematically for us. The only thing which is important, that this is not zero. It means that in mathematical setting, as I told you, the bracket here, let me show you here, this bracket is not zero. This is equivalent to each. So as I wrote it again in this picture, here, this bracket is not zero. It means that the variation of the position and momentum are not zero. And this is something that the physics are working on that, because this problem is a very good problem in the physics to study whole body problem. This is a problem that they are working on that.
Okay, thank you very much, Professor.
Okay.
Thank you very much.
Thank you, Hernan, for your question. More question? So, Professor Razani, thank you very much for this very nice talk. And now, on behalf of the organized committee, I would like to invite you all the upcoming seminar that will take place on March 5th with Lorena Bossio from USA and Gabriel Barrenechea from Scotland. So everybody will be invited. Thank you very much, Razani. Ciao.
Thank you. Thank you. Ciao. Ciao. Thank you. Thank you so much. Thank you.